Welcome to your second video on electric fields. In this video, we're going to just continue off our first video, except we're going to be focusing more precisely on quantitative calculations. So in this video, we're going to be focusing mostly on points in proximity to 1, 2, or maybe 3 spheres giving off electric fields. And how does it affect, and how are the electric fields at that point? So let's take a look at my first example. We have two positively charged plates, A and B, with charges of 1.5 times 10 to the negative 6 coulombs and 2.0 times 10 to the negative 6 coulombs, respectively, are 3.3 times 10 to the negative 2 meters apart. We want to determine the net electric field at point P midway between the two plates. So the first thing we should have is a diagram to help us understand this question. I have two positive spheres with a point placed directly in the middle of them. Since they're positive spheres, I know that electric field lines are going to be going away from them, just like this. So they're constantly going to be away from both. That means both of these lines, you might say, are pushing this point away. So the electric field of B on the point is going to be pulling that way. And the electric field of A on the point is going to be pushing this way. It's not going to be quite as big. So we're going to have to subtract the two electric fields between these 2 points. We know the distance from them is the same, but B is stronger than A, so its field line is going to be a bit bigger. So let's try this out. First, what are we given? We are given the charge A is equal to 1.5 times 10 to the negative 6 coulombs. We are given charge B is equal to 2.0 times 10 to the negative 6 coulombs. And we're given the radius is 3.3 times 10 to the negative 2 meters. But if we remember, it's right in between each of them, so if we're really looking at my distance of this point, it's going to be half of 3.3. So that means it's going to be actually 1.65 times 10 to the negative 2 meters is going to be my distance between each sphere. Now I know my equation for, let's look at point sphere A first, is going to be equal to Coulomb's constant multiplied by charge A divided by the radius of A to that point squared, which is going to give me 8.99 times 10 to the 9 newtons meters squared per coulomb squared multiplied by 1.5 times 10 to the negative 6 coulombs, all divided by 1.65 times 10 to the negative 2 meters squared. This is going to end up giving me 4.953 times 10 to the 7 newtons per coulombs. Now let's try my second charge, charge B. So for charge B, I had my field strength on that point is going to be the Coulomb's constant multiplied by charge B divided by the radius squared, which is going to give me 8.99 times 10 to the 9 newtons meters squared per coulomb squared multiplied by 2.0 times 10 to the negative 6 coulombs, all divided by 1.65 times 10 to the negative 2 meters squared. Now this is going to give me 6.604 times 10 to the negative 7 newtons per coulombs, and this one's going to be to the left, so I'm going to put this one negative. So now we're going to use vector addition to figure out the net electric field. So my net is going to be, we're going to have the electric field strength of A from charge A plus the electric field strength of charge B. So we have 4.95 times 10 to the negative 7 newtons per coulombs right plus negative 6.604 times 10 to the 7 newtons per coulombs left, which will give me a total of 1.6 times 10 to the 7 newtons per coulombs left. So our second example today is going to be in 2 dimensions. In this example, we are to calculate the net electric field at point P, that is 4 times 10 to the negative 2 meters from a small metal sphere with a negative charge of 2.10 times 10 to the negative 6 coulombs. and 3.0 times 10 to the negative 2 meters from another similar sphere with a positive charge of 1.5 times 10 to the negative 6 coulombs. So let's take a look at my picture here. If you're stuck, remember to always draw a diagram because it can always help. So let's first look at sphere A. Sphere A is negative, so that means the electric field lines are going to be going towards sphere A. So from point P, my sphere lines are going to be that way. This is going to be my electric field of A. Now if I look at B, they're going to be going this way. And this is going to be my electric field of B because it's positive, so it's going to be going away from everything. Now looking at this here, this looks like we're going to end up needing vector addition, which we will. But first thing I'm going to do is I'm going to first look at charge A and figure out what is the magnitude of that vector. And then I'm going to look at charge B and figure out the magnitude of that vector, and then separate them both into their x and y components. So what's given for A? First, for A, we know that my charge A is negative 2 times 10 to the negative 6 coulombs. I know my radius is 4.0 times 10 to the negative 2 meters. And I know my angle is 36.9 degrees to the horizon. Now let's look at charge B. For charge B, I know that the charge is equal to 1.5 times 10 to the negative 6 coulombs. I know that the radius is 3.1 times 10 to the negative 2 meters. And I know my angle, 53.1 degrees. So now let's try and figure out what is the magnitude of the electric field vector for charge A at point P. So we know the electric field for A is equal to Coulomb's constant multiplied by the charge of A divided by the radius of A to P. That's going to give me 8.99 times 10 to the 9 multiplied by 2.1 times 10 to the negative 6, all divided by 4.0 times 10 to the negative 2. And we have to square that, which ends up giving me 1.18 times 10 to the 7 newtons per coulomb. So now let's break this angle down to its x and y components. I look right here, this angle 36 is going to be the same as the angle right here, 36. So I'm going to use Sir-Coxeter-Tix, where cosine, since we're coming off the x, I'm going to use Sir-Coxeter-Tix, where cosine is going to be my x value and sine is going to be my y value. So let's first look at my x component, and that's going to be cosine. So I'm going to have my x component of the field is going to be equal to 1.18 and times 10 to the 7 newtons per coulombs cos 36.9. And that's going to give me a negative number because I know it's going to be going to the left, which is going to give me negative 9.436 times 10 to the 6 newtons per coulombs. Now let's look at my y value for A. My y value is going to be 1.18 times 10 to the 7 newtons per coulombs multiplied by sine 36.9. And that's going to end up giving me a negative 7.085 times 10 to the 6 newtons per coulomb. And once again, the x and y vectors here are going to be negative because if we look at it, we're going down for my y and we're going to the left for my x. So now let's try and find the magnitude of the vector for the electric field of charge B at point P. So my formula is magnitude of the electric field is going to be Coulomb's constant multiplied by charge B divided by the distance of point P to charge B squared. That's going to end up giving me 8.99 times 10 to the 9 newtons meters squared per coulomb squared, all multiplied by 1.5 times 10 to the negative 6 coulombs divided by 3 times 10 to the negative 2 meters squared. And that's going to end up giving me a total of 1.48 or 1.498 times 10 to the 7 newtons per coulomb. So now let's break vector b into its x and y components. Now if I look at this here, we are still going to be going off the x right there for vector b. And it's going to, this 53.1 is going to just move there. So we're going to use Sir Coxeter again. In this case though, if we look at it, my x component is negative because it's going to the left, but my y component is going up, so it's going to be positive. So let's try that out here. Let's first break it down into its x component, and we're going to use Sir Coxeter. So in this case, I know my field in the x is going to be equal to, and it's going to be a negative, 1.498 times 10 to the 7 Newton per coulombs multiplied by cos 53.1. And that's going to give me negative 8.994 times 10 to the 6 newtons per coulomb. Now let's look at my y. My y is going to be positive. So my y vector for the field of B is going to be 1.498 times 10 to the 7 newtons per coulomb sine 51, because we're using Sir now, which is going to end up giving me 1.198 times 10 to the 7 newtons per coulomb. So now let's combine my x components. So I'm going to have the net electric field in the x is equal to the electric field of A in the x plus the electric field of B in the x. Now both of these are going left, so my sum is going to be a negative and each vector is a negative. So we have negative 9.436 times 10 to the 6 newtons per coulomb plus negative 8.994 times 10 to the 6 newtons per coulomb. And that's going to end up giving me negative 1.843 times 10 to the 7 newtons per coulomb. So now that we've found the magnitude of my electric field in the x, let's look at the y. So for the y, we're going to have to look at the sum of sphere A and B's magnetic field at point P. So I'm going to end up getting negative 7.085 times 10 to the 6 newtons per coulombs for A, and for B, it's positive because it's going up, it's going to be 1.198 times 10 to the 7 newtons per coulomb. When I combine these together, I'm going to get a total positive field of 4.895 times 10 to the 6 newtons per coulomb. So now let's combine my x and y to make a resultant. So we're going to look at this x here, this y here, and make our resultant. So I'm looking at this to my x means I am going to end up going to the right. And my y is negative or positive, so that means I'm going to go up. So my resultant vector is going to be something like that there. So we're going to use the Pythagorean theorem, which is going to be x squared plus y squared is equal to r squared to find my resultant. So it's going to give me 1.843 times 10 to the 7 newtons per coulomb squared plus 4.985 times 10 to the 6 newtons per coulomb squared, and we're going to square root that all to end up getting 1.91 times 10 to the 7 newtons per coulomb. Now we have to find my angle. So that angle is going to be, I'm going to use tan, which is going to be in this case y over x to figure out what my angle is, because we want to always come off the x, and that's going to be 9.5 times 10 to the 6 divided by 1.483 times 10 to the 7 newtons per coulomb. That's going to end up giving me 14.9 degrees. So overall, I end up getting 1.91 times 10 to the 7 newtons per coulomb at an angle of 14.91 off of x, or a total of 165 degrees rotation, which is 180 minus 15 to get 165 degrees. So let's review what we did here. We first started off and I had to find what is each vector. So we looked at our vector for the field of A, and then we looked at the vector for the field of B. Then what I did was I tried to break down the A vector into x and y, and then I broke down the B vector into x and y. Then we combine my x vectors together for the fields, and we combine my y vectors together for the fields. With that then, I could figure out, use the Pythagorean theorem, to figure out what is going to be my resultant when I add these two vectors together. And from there, I could then also get my angle using tan. And that is how we solve this question. So there's several steps to it. First, find my vectors from each sphere. Next, we're going to break those vectors into x and y. Then we're going to combine all the x vectors together. Then we're going to combine all the y vectors together. And then what we're going to do is find the resultant using the x and y together to find the resultant. And then we're going to find our angle once we know my total x and my total y.